In this video, we're going to talk about the Cauchy integral formula on a circle and some applications, the main application being the proof that holomorphic functions are automatically analytic. The first thing we need to do is define complex line integrals on circles. Now later on we're going to go into more depth on exactly what complex line integrals are, but for now it's just easy enough just to define some notation. So we start with a continuous function on a circle of radius r centered at z0, and we're going to define this object, which again we'll go through more detail of what exactly this means, but for now we can just take it as a definition that we're going to parameterize the circle via theta with z equals z0 plus r e to the I theta, and you put that in for z, and so dz will become basically a derivative of this. So we have ri e to the I theta d theta, and that's how we get our definition of the complex line integral. So we have theta going from 0 to 2 pi, so we go around the whole circle. And this is a way of integrating a complex function in the complex plane, and we'll have more general definitions of this for all kinds of curves later on, but this is just for a circle because if we do this just for circles right now, we can get some nice applications and we can go into more detail on line integrals later. There's also something called an arc length integral on the circle, which we define with an absolute value of dz, which just means that we take the absolute value of this expression here and you just get r. So in case you're not familiar with integrating complex valued functions, it's just as easy as can be. If I have u plus iv as my complex valued function, you just integrate the real and imaginary parts separately. Some things that you would have to go through a little detail to show is that this is actually complex linear. So if I had alpha, a complex number, and if I had f, a complex valued function, that you can pull the alpha out of the integral, and that's just a matter of doing the multiplication and checking that. One important fact we'll use a number of times is that a complex integral in absolute value is less than or equal to the integral of the absolute values. And this, in the context of our integrals on circles, will say that our complex line integral on the circle here is bounded by the modulus of f integrated with respect to arc length, so that's important. It's not just some kind of dt like we had up here. You have to do an arc length integral, and this in turn we can bound by the supremum of f on the circle, and you get the length of the circle 2 pi r. Now this fact takes a bit of work to show, but it's not difficult either. So I'll leave it as an exercise. Here is the Cauchy integral formula on a circle. So we start with a holomorphic function on the circle of radius r centered at z0. And for any little r less than big R, we need to move in a little bit. For any z in the disk of radius r centered at z0, we can compute the value of f at z using a complex line integral. And here's the formula. So this is important to get used to or memorize. You have f of w over w minus z dw. So again, this is a complex line integral using w as my complex variable. I guess you do have to, there is some kind of dependence in the notation on knowing that you're dealing with a complex variable. And this is really powerful because it'll basically show that f has the same sort of regularity and nice properties as 1 over w minus z. Now, why is this Cauchy integral formula on a circle? Well, there's going to be a very general Cauchy integral formula that we see later, and typically complex analysis books go through stages where they prove maybe a Cauchy integral formula on a triangle or a rectangle and then a circle, and then they go through all of these different steps. Here we're going to do an approach where we just have to do this one on a circle to get a bunch of nice properties about holomorphic functions, and then later we can prove the more general versions. So to prove it, we need a bunch of lemmas, and maybe we'll go through the lemmas and show how they prove the theorem, and then we can go back and prove all of the lemmas. So this first lemma says that we have a holomorphic function on this annulus, so this is just points in the plane in between with modulus between little r and big R. And if we define these integrals depending on the radius, so here t will be between little r and big R, and I'm integrating f around a whole circle, then this turns out to be constant as a function of t. The next lemma that we need is a special case of the Cauchy integral formula on a circle. So here it is. So this is just the special case of f identically equal to 1, but I've specialized it to the unit disk, but that's no big deal. So for z in the unit disk, the integral of 1 over w minus z dw, 1 over 2 pi I, will give me 1. That's exactly what we have up here if you put in 1 for f and little r equals 1. What's the other ingredient we need? This is something about the difference quotient function. If I have a holomorphic function on some open set or a domain, I'm going to define this difference quotient function, capital F, on u cross u, and it's given by little f. It's the little f's difference quotient, f of z minus f of w over z minus w when z is not w, but it's equal to the derivative when z equals w. And our claim is that this is a continuous function on the product set. Now let's take these three lemmas and prove the Cauchy integral formula on a circle. So here's the proof over here. Let me get it all together so you can see the Cauchy integral formula. Okay, so we'll start by assuming, without loss of generality or by translating and rescaling, that z naught over here is just 0 and little r is 1 and less than big R. So first thing we do is we define capital F as in this lemma here as this difference quotient function when z is not w, but it's equal to the derivative when z equals w. And I'm going to integrate big F with respect to w, but I'm going to leave z fixed. Now, big F is a continuous function, so the nice thing about it is we can kind of attempt to integrate past the so-called singularity when z is w. So to integrate big F with respect to w on the circle of radius t, I'll view that as a function of t right now. And this does depend on z, but again, I'm saying that z is fixed. Okay, so the definition of this complex line integral is just this. So you put in t e to the it in for w, and when you take the derivative of that and cancel i's, you'll get t e to the I theta d theta over 2 pi. Okay, the first thing to point out is that since capital F is continuous, this function h as a function of t is continuous in t. So this is something from real analysis. Since f is jointly continuous, it'll be uniformly continuous, and so there's no issue of the continuity of this function of a parameter after you integrate it. Okay, and then so that's partially using this lemma right here about the difference quotient function. Now I need to point out that capital F is holomorphic as a function of w, at least when we stay away from the singularity. It turns out it will be holomorphic at the singularity, but that's not something that we'll worry about right now. So if w and z stay away from each other, so if w is strictly less than z, or if w is strictly greater than z in modulus, we just have this function here. And so as a function of w, we're going to get something holomorphic, because it'll just look like our holomorphic function divided by z minus w. And this is the function we're integrating with respect to theta, and so this is where we're going to apply this first lemma. So by this first lemma, h here will be constant in these ranges where we know the function that we have is holomorphic. So it's constant for t between 0 and modulus of z, and it's constant in the other range where we know it's holomorphic. That's for t between modulus of z and 1. Okay, but now we just point out that, well, h is continuous and it's constant on these two intervals right next to each other. So the value at 0, which happens to be 0, just plugging that in, matches the value at modulus of z, which matches the value at 1. And so this is the main effect that we need, since we've reduced to the case where little r is 1 and z naught is 0. So what does this fact say? If you separate things out, you get the complex line integral that we're interested in is equal to another integral, but we can pull the f of z outside, and then we get this integral here. And by the second lemma, which was right here, by the second lemma, this integral here is just 1, and so we get the formula that we wanted, which was right here. Specialized to the case little r equals 1 and z naught is 0, but again, that you can get that from translating and rescaling. In the next video, we'll complete the proof by proving all the lemmas.